Welcome to the 53rd Theoretical Physics Colloquium by Kirill Tuchin from Iowa State University. He got his PhD in 2001 from Tel Aviv University. After that, he had a postdoctoral position at the Institute for Nuclear Theory at the University of Washington between 2001 and 2003. Between 2003 and 2005, he was a postdoc at Nuclear Theory Group at Brookhaven National Lab. He also became a fellow of Riken Biennial Research Center at Brookhaven in 2005. And in the same year, he became a faculty at Iowa State University, where he is now. In 2000, he received prize for research achievements from the School of Physics and Astronomy at Tel Aviv University. He had this fellowship at Riken Biennial between 2005 and 2010, and he received several times the Most Valuable Classroom Instructor Award at Iowa State University. His research interests include high energy particle and nuclear physics, strong interactions at high energy and temperature, perturbative and non-perturbative aspects of QCD, highly intense fields, quantum electrodynamics, quantum anomalies, and many other things. And today he will be talking about electrodynamics of hot nuclear matter and other chiral media. And with that, I'll give the microphone to Kirill. You may start sharing your screen.
Okay. Thank you, Igor, for this nice introduction. Probably you are the only person who read my resume now. Can you see it?
Yes.
Okay, great. Yeah, thank you, Igor, for inviting me to give this colloquium. And the whole series is very nice, and especially during these difficult times. It has been a great opportunity to learn what other people do without traveling long distance. I'm going to talk about electrodynamics of hot nuclear medium. And the part of my title that says that other chiral media means that many of the conclusions that I will obtain for hot nuclear medium also apply to other chiral media. Okay, so the outline of my talk, very briefly, I am going to talk about two kinds of electromagnetic fields generated in relativistic heavy ion collisions. One is external classical field generated by colliding ions. This is a highly intense field, maybe the most intensive field ever generated in the universe. And the other type is quantum excitations that are built into the quark-gluon plasma. So I'll talk about both, and I'll indicate what I'm talking about on a particular slide. One of the foci of my talk is to discuss the electrodynamics in the presence of the chiral anomaly. And a disclaimer, this talk is not supposed to be a comprehensive review of this subject, but rather it strongly reflects my personal interest in this field. Okay, let me begin with talking about generation of this classical electromagnetic field. What you see here, say in this corner, in the left corner, is that two heavy ions collide each other at almost the speed of light, and this is why they look like pancakes. And on this TZ diagram, Z is the collision axis. You can see the two heavy ions approach to this point. And at t equals to 0, the electromagnetic field generated by these heavy ions is essentially the total sum of all Coulomb fields of each individual nucleon, each individual proton in the nucleus. And this is basically this boosted Coulomb field. You sum up all these Coulomb fields, and you very quickly realize that the strength of this field is of the order of 10 to 18 Gauss, okay, which is about 3 orders of magnitude the strength of the magnetic field in magnetars, and its strength is of the order of the strong interactions. So we expect that this field is important in the quark-gluon plasma. Okay. Now, the real question is, of course, is not what was the field at t equals to 0, but at the moment of the collision, but what is the field after the collision, because that field is what actually influences the plasma. And to answer this question, we need to study the matter distribution after the collision. The experiment shows, and theory supports this conclusion, is that most of the matter produced in the heavy ion collision sits in this so-called mid-rapidity region over here. And the valence charge, the electric charges, travel in the forward and backward direction. So essentially, the electric charge travels away from the quark-gluon plasma and creates electromagnetic field in it. So to compute it, we need to solve complicated magneto-hydrodynamic equations. However, in the first approximation, we can estimate these fields by simply noting that electromagnetic interactions are weakly coupled to the plasma, just because plasma is strongly interacting. And then as a first estimate, you can solve the Maxwell equations and insert in these Maxwell equations the external sources, those valence charges I mentioned before, and also the currents induced by this external field inside the plasma. Now, at first sight, you can think that these induced currents are very small because the conductivity is known to be very small. The latest calculations show that the electrical conductivity is of the order of 6 MeV at the critical temperature. And if you compare this to the typical QCD scale of 200 MeV, right, it's typical temperature, then you may think that it's not important. But however, it's not the correct conclusion, because if you solve this equation, basically solve the Maxwell equations with sources on the right-hand side, you'll get this solution here. So the magnetic field is given by this rather simple formula. I'll try not to show complicated formulas in this talk. But this formula is nice because it's just one integral and shows the magnetic field of a point charge. The relevant parameter here is this combination, which is gamma factor, the Lorentz gamma factor of the valence charges, the electrical conductivity, and B is an impact parameter or typical transverse distance between the colliding ions. So if this parameter is small, then you go back to the Coulomb field in vacuum, and basically the fact that plasma has any conductivity is not important. However, if this parameter is of the order of 1, then the solution is different, and you can see it falls off with time. So this x minus is essentially time, falls off as time squared, while the vacuum solution is time cubed, and you can see the difference here, right? So basically what it means that the electromagnetic field is frozen into plasma, and therefore it influences plasma much more than it would have been in vacuum, right? So basically this effect is due to the time dilation, relativistic time dilation, which causes the effective scale to be not 1 over sigma, but 1 over sigma gamma. Okay, so the effective time scale is much shorter than in static case. Okay. Now, this is can be, of course, computed with high precision. What I showed you so far was just point charge. If you put all the charges, include the realistic distributions, you can show that the field, the electromagnetic field created in heavy ion collisions is mostly magnetic. I'm sorry, mostly magnetic, but there is some small electric part as well to it. In what follows, I usually assume that magnetic field is roughly constant and usually neglect electric component at all, unless I will mention it. Now, so far, I assumed the calculation was very simple and assumed that this electromagnetic, this electric charge is coming from infinity and move essentially forever in plasma, right? So it's the solutions that start from infinity, move in plasma, create the field. So there's always infinite time for electromagnetic fields to build up. So all the retardation effects are not so important. But this is not the case. The actual situation is that at time t equals to 0, you have the initial electromagnetic fields, and then you let these fields evolve in medium. And to solve this problem, you need to solve the initial value problem. So this is what is written here. This equation here is for the vector potential. And these two equations set the initial conditions for the electromagnetic field, which is determined by the vacuum, the Coulombic fields basically that existed at t equals to 0 at the moment of the collision. And then you have to propagate this solution into the plasma. This is the solution of this problem, the initial value problem. And G2 here is the Green's function that consists of two pieces. One piece is the original pulse, basically usual point charge contribution, suppressed a little bit by this dissipation due to finite electrical conductivity. And the second piece is the wake. Okay, so this is the wake, this is the pulse here, and the wake is here. The wake is turns out to be very small because it is proportional to the conductivity squared. If you remember, the conductivity is a small parameter. It's not multiplied by any gammas here and can be neglected. So this, I'm going to show you the calculation done by my student, Evan Stewart. So what turns out that is shown here that the electromagnetic field as a function of time at some selected impact parameter is even more frozen than we thought. This is the red line, is almost constant, assuming that the plasma emerged at some initial time over here. I think it's 0.2 Fermi or something like that. If you allow the plasma to build up over a longer time, these are this dashed and dotted line, you'll have a little different distribution of the field. But basically, all it shows you the uncertainty about the value of magnetic field in the plasma. Yes.
There is a question.
Yes.
Okay. I wanted to ask about the scale of minus sigma delta t that you showed in the previous paper, previous slide. I mean, isn't it small for the quark plasma?
This one?
Yeah.
Yeah, it is small.
So it's not, the terms are not suppressed that much, yeah?
Yeah, there's some retardation effect there, of course, it influences, but in general, you can say that it's relatively small, yeah.
Thank you.
Yeah.
Can I also ask a quick question? It's about the electric field. I think people have discussed the strong electric field and Schwinger pair production. Is that a possibility here?
Well, just to answer this briefly, it's not a possibility here because the volume of plasma is too small for that. For Schwinger mechanism to work, you need much higher volume so that the wavelengths of the Compton wavelengths of electron fit in this volume. Right? If you want to produce higher, heavier particles, then it requires stronger electric field, but then smaller volume.
I see. Okay.
So simply speaking, the wavelengths of electron doesn't fit into the quark-gluon plasma. That's it.
Okay. Okay. Thank you.
Okay. So now, of course, I am interested in is what kind of effects are produced by this field on plasma. And first, I'll mention non-chiral effects, and then we'll move to chiral effects. I will, again, as a disclaimer, I am not going to cover everything. It's impossible. It's a huge amount of work done by many researchers. I'll mention only two effects that again dear to my heart. The first one is synchrotron radiation. If you put fermions in the magnetic field, the motion in the perpendicular plane is quantized. And then when the electron jumps from one level to another, it emits radiation. In a strong electric field, in a strong magnetic field, I'm sorry, you can even see the different discrete Landau levels. This is because the distance between the Landau levels is this EB over energy of particle. If it becomes larger than the thermal width, then you can, in principle, resolve these individual levels. Maybe not at current energies, at least not a trick, but maybe in future it can become possible. So this is the spectrum that is produced by this synchrotron radiation. You can see very strong enhancement in the infrared, and that may be one of the missing contributions in the total spectrum of photons produced by quark-gluon plasma. And what this picture shows at the bottom is that synchrotron radiation has been considered as one of the possible sources of gamma ray bursts by collapsing stars. And actually, I had a very interesting discussion about this with astrophysicists. Okay, another effect that this magnetic field induces is it breaks the bound state. We know that quarkonia, the bound states, are thought of to be as kind of thermometers of quark-gluon plasma. By looking how these quarkonium states dissociate, you can learn something about the temperature of the plasma. This is not that easy actually, because this quark-gluon plasma is subject to extreme conditions. And one condition discussed in this slide is external magnetic field generated by these heavy ions. There's also rotation of the whole plasma. So the question is, how does this whole thing, all these external conditions influences the decay rate of the a bound state? And to answer this question, we go to the rest frame of the, let's say, J psi. It actually can be any bound state. And in this rest frame, you have an additional electric component of the electromagnetic field. And this electromagnetic field can ionize the bound state by pulling quark and anti-quark in the opposite directions. So there's finite probability to decay. And this is illustrated in this simple sketch. This is the binding potential of a J psi, and this is the potential of the electric field. This quark or anti-quark can tunnel through the potential barrier and escape to infinity, which would be the destruction of the dissociation of J psi. Right? And you can compute the rate, the probability of this to happen, and this calculation is actually part of the probably any textbook in quantum mechanics. But what we want to do is to actually include the rotation there and magnetic field. The magnetic field component in the bound state frame also plays a role in this situation. What you can see here is the effective potential as a function of magnetic field. The larger magnetic field, the wider is this potential. And therefore, a bound state, say a quark, will tunnel through the wider potential at stronger magnetic field, and therefore the probability to decay is smaller. Now, if you now consider rotation, what is shown here is negative charge rotating in the magnetic field counterclockwise, and we would like to look at this process in the frame rotating with angular velocity omega. So if you sit in this frame and look at this charge, you will see it will appear as rotating with much smaller frequency than in the lab frame. And opposite, if you look at the positive charges, they appear to be rotating much faster. So you can conclude, or this person in the rotating frame can conclude that the synchrotron frequency for negative charges is smaller than the positive. So magnetic field is smaller than for negative than for positive charges, and therefore the dissociation probability is larger for negative charges. You can do the calculation basically using the imaginary time method, which is earlier incarnation of worldwide instanton formalism. Essentially, you compute the trajectory, the classical trajectory under the potential barrier, evaluate your action on this trajectory, and this gives you the decay probability. Okay, so as I mentioned, basically to summarize what I said is we can look at this probability versus rotating frequency divided by synchrotron frequency, we see that the faster the bound state moves in with respect to the plasma, the stronger is the effect of magnetic field. And this is because the electric component is proportional to this velocity in the quark-gluon rest frame. You can see that the larger, the faster the rotation, again, the larger the probability that the bound state decays. You can see that there is a difference between the negatively charged particles and the positively charged particles. This obviously breaks parity and C and B symmetries in the plasma, and this is not surprising because magnetic field in these heavy ion collisions points in the same direction as the angular velocity, right? So omega and B is in the same direction, and this causes this asymmetry between negative and positive charges. So as this is the difference between decay probability of negative and positive charges, which implies, for example, that you're going to see more D pluses than D minuses in the final spectrum. And similarly, yes.
Quick question. When you're talking about the total charge, you're talking about the total charge of the bound state, right? This plus and minus signs.
Yeah, yeah. So in this model, this model I consider a potential as basically delta function, short range potential, and there is a particle, say light particle. If you have d meson, you take one d quark, which will tunnel, and the heavy quark will not tunnel, or the probability for it to tunnel is much smaller.
But it seems like the fact of the spin orientation of the bound states is much more important in the present magnetic field than just the charges. Isn't that the case? So let's say same spin or opposite spin, they will be very different bound states.
Sure, yeah. This is purely classical calculation, so or quasi-classical, right? So I didn't take this spin effect into account. But it's a good point. It should be also an interesting effect to consider. Absolutely, yeah. Okay. So if you want to read a little bit more about this, you can look in the archive. So there are many other interesting effects of B on QGP discussed in the literature. I just cannot possibly review all of them, and so I'll stop here and move on to discuss the Chiral anomaly and the chiral magnetic effect and the effect, the influence on the electrodynamics in hot nuclear medium. Well, first of all, let me give just a brief introduction for the sake of the graduate students who might be watching this presentation as well. The chiral symmetry of nuclear matter is your left cross your right, given by this decomposition. A1 of this symmetry is broken by anomaly. Okay, so it's axial symmetry broken by anomaly. The axial symmetry is this transformation here. And the breaking of the symmetry is due to the non-vanishing divergence of the axial current, which signifies that the number of right and left-handed, the difference between the right number of right and left-handed quarks is not conserved. Okay, this integral on the right-hand side is known as magnetic helicity. As a consequence of this anomaly, the neutral pion will decay into 2 photons or 2 gluons. And in the same way as electromagnetic field is coupled to pi 0, it also couples to other axial currents, such as axion, for example. Now, we know that the QCD vacuum is a superposition of states with different topology. And this is the topological charge density that characterizes this topology of the system. If you integrate it over space-time, you get this, what is called Chern-Simons numbers, characterizing each minimum of QCD, and the transition between this minima creates a local imbalance of chirality. These transitions are very important at high temperature because this transition rate between different minima is proportional to T to the 4th. So it is expected to play a major role in the dynamics of the quark-gluon plasma. Another point that we need to take is that it has been shown in many lattice calculations, and also theoretical work has been done on that in the QCD vacuum may contain topological domains with finite topological charge, which can be as large as a few Fermi. Right? It can be actually even at 0 temperature, but certainly at the finite temperature. And so the photon field couples to these topological domains. And what I'm going to discuss is the result of this coupling. What would you expect if this coupling happens? Okay. And the tool the most convenient tool to discuss this physics is the so-called Maxwell-Chern-Simons theory, which essentially couples electrodynamics to an effective pseudoscalar field theta. You can call it axion field if you want, but for the purposes of this discussion, it is a field that describes the topology of these domains in quark-gluon plasma. The effect of this field, very shortly, is to induce a current in the different currents in the right-hand side of this Ampere law. This current tells you that there is electric current generated in the direction of the magnetic field, and the coefficient of proportionality, sigma chi, is called the Chiral conductivity, and I will use it a lot in the following presentation. And the interesting thing about this Chiral conductivity is that it's P odd and T even, so it describes a non-dissipating current. And if you have such a current in plasma, and also you apply the magnetic field I was speaking about before, this magnetic field will drive the positive charges and negative charges in the opposite directions. So this effect is known as the charge separation effect, and in principle should be observable quantity in heavy ion collisions. Okay. So other notations that are frequently used is time derivative of the theta is denoted is called the chemical axial chemical potential V5, and the B, this parameter, the vector B, which is proportional to the gradient of theta, is measures the asymmetry of the anisotropy of this plasma, and in Weyl semimetals, for example, it places its distance between the Weyl nodes in momentum space. Okay, but throughout this talk, I usually will ignore this inhomogeneity and only focus on this time derivative. But sometimes I will mention the effect of various chiral effects in Weyl semimetals, and then of course this gradient of theta will be non-zero. Okay, there's another piece here, another current, so-called anomalous Hall effect, that again, as I mentioned, I am not going to discuss, even though it's very interesting too. The experiment has been done, and it's being done actually to measure the charge separation. It's not conclusive, and to the best of my knowledge, it's still an open question because of large background and heavy ion collisions. Though in Weyl semimetals, probably drug semimetals, this the Chiral magnetic effect has been observed, and this is due to the finite gradient of theta. Okay. What is my intent here is to study the effect of the Chiral of this Chiral magnetic effect on the electromagnetic field. So, and the first thing to do is to insert this Chiral current into Maxwell equations, right? So you have this Chiral term here, and we want to know what are the possible excitations of electromagnetic field in plasma. It's not difficult to solve this equation, dispersion relation, and you find that out of these four solutions, there's always one solution with whose imaginary part is positive if the wave number of this excitation is smaller than this Chiral conductivity. Okay, so if this condition is satisfied, there's always a positive imaginary part of some omega, which drives the instability of magnetic field. And this instability plays a very important role in many models of the early universe evolution, the production of cosmological magnetic fields and so on. So for my interest here is to find how this magnetic field evolves in the plasma environment, right? So this instability has been observed, of course, a long time ago. This probably the first time I know that it has been noticed. So they noticed that the Green's function contains a causal piece here, and of course this is the causal piece that emerges because if you take the integration contour along the real axis, but if you go take the contour around the poles, above the poles in the upper half plane of complex omega, then instead of a causal but stable solution, you get causal but unstable. So either way, it's a signature of instability in this model. Now, the interesting fact is that the instability that appears in this magnetic field is not tamed by energy conservation. If the magnetic field can grow as much as it wants, and still the energy is conserved. What tames this growth, among other things, is the Chiral anomaly, the conservation of total helicity as implied by the Chiral anomaly equation. Assuming that the medium is homogeneous, you can show that total helicity is conserved. This is shown in this equation. This term here is proportional to the density of chiral charges in medium. Basically, this whole term is total helicity of medium. This term here is magnetic helicity, this integral here, E dot B. And the sum must be constant. Okay. So it's we want, if you add to this the equation of state, you can in principle solve this constraint and find how the magnetic field evolves in medium. So the simplest possible model to consider is to consider the plasma in a box, right? And write down the decomposition of the vector potential in the normal modes. These W's are eigenstates of the curl operator. And the amplitudes, then some of the amplitudes grow exponentially with time. And because of that, you can find one mode that is divergent the fastest, okay, and it's given here. And if you follow the evolution of this mode basically drives the instability of the entire field. So if you follow the divergence of this mode alone, you can write down a simple differential equations that satisfies the helicity conservation condition, meaning that total helicity in plasma plus total helicity in the field is a constant. Okay, and this equation is, you see, it's a very simple equation to solve. Alpha is some dimensional parameter determined by the equation of state and the volume and so on, but it's just a number. And the solution to this equation is shown here. Essentially, the fraction of total helicity in plasma decreases and moves to, and all the helicity is transferred to the field. And as long as this process continues, the magnetic field grows in time. And there are two scenarios. Now, in one scenario, magnetic field grows in time and then decreases. And in another scenario, the instability never emerges in the first place, and the magnetic field always decreases. And it's interesting that in this particular model, the instability occurs if the fraction of initial helicity in medium is more than 50%. Okay, so if there's enough initial helicity in medium, then magnetic field simply sucks it and grows until it sucks up all the helicity, and at which point it starts to decrease. Okay, and you can consider more complicated models, but I think in most of them you see the same kind of qualitative picture. An interesting extension of this model is to consider the role of magnetic monopoles. It was suggested by Chirac in 2009 that magnetic monopoles may play an important role in quark-gluon plasma, even at temperatures above the critical temperature. And if so, the question becomes, what role do they play in this magnetic field evolution in plasma? And this has been discussed by a student at the time, Yang Li. I won't show you all the details, but the conclusion we came up is that because in the presence of magnetic monopoles, the evolution always ends up in a superconducting state. It's always superconducting current there. Once the magnetic field stabilizes and the divergence disappears, the system ends up in the superconducting phase. Okay, so far I spoke about evolution of magnetic field at finite chiral conductivity. Essentially, I picked up my favorite vacuum here in this picture and say, okay, let's see what magnetic field does there. Obviously, you cannot follow this evolution for longer than it takes for the field configuration or the gluon field configuration to change and jump to a new vacuum, right? So as long as you can believe that you're sitting in the same vacuum, you can follow the evolution of magnetic field. But once your system jumps to a new vacuum, you now need to solve a new equations, right? So the typical Floréron transition time is given here. G is thermal coupling, T is temperature, and you can evaluate the divergent exponent and show that it actually never ever grows big enough. So there's no actual instability. But the question then becomes, what happens in a long time? Suppose you wait a long time. Will the electromagnetic field diverge or not? Will it show any instability? And to answer this question, I developed a very simple model. I simply consider the chiral conductivity as a stochastic process with the average being 0 and the dispersion being proportional to the axial chemical potential, and the correlation time being shorter than this Floréron transition time. Okay. With these ingredients, you can actually solve this problem. Okay. It turns out that the amplitude of the magnetic field is a solution to a simple differential equation with random frequency. So this x is proportional to the field amplitude, and this psi is a random variable. So solving this problem amounts to solving a harmonic oscillator with random frequency, and it turns out it can be reduced to integral differential equations. So this u is some vector containing these various derivatives of x, and A naught and B are some matrices. And using the approach developed by Van Kampen, you can write down a differential equation satisfied by expectation values of this x and its derivatives and powers. For example, the differential equation satisfied by the expectation value of this x, field amplitude, remember, is shown here, where C1 and C2 are certain moments of the correlation function. Right? Now, solving this equation, you can convince yourself that the field amplitude is never unstable. Okay? In a long time, if you wait a long enough time, the field amplitude is never unstable. The magnetic field is always stable, always decreases to 0. Okay, there's no instability, at least for the parameters of the quark-gluon plasma. But this is concerning the amplitude of the field. What about the amplitude square of the field, right, which contributes to energy? Well, you can actually solve this problem as well. And for simplicity, I assume that the correlation function has this form, and I computed all these correlation coefficients. It turns out that the good conductor, it always damps any instability. But the poor conductor, which remember I mentioned before that the quark-gluon plasma is actually a poor electroconductor, then instability can emerge. And this is the formula that for the expectation value of the energy modes with given wave vector and helicity shown here. You can see that sometimes if this parameter here, this combination is bigger than the conductivity, then the instability can develop. But the interesting point here is that this formula does not depend on helicity at all. So even though we started with chiral magnetic effect, we found that that long times the divergence that may actually arise in the system has nothing to do with helicity at all. In other words, the right-handed modes and the left-handed modes have divergent helicities, but their total sum is zero, because they come together with opposite signs. Total helicity, average total helicity is zero. So if there is instability, it's not chiral. And if you plug in some numbers for quark-gluon plasma, this is the region where instability can develop, and it can reasonably occur even in photoparameters we have presently in, say, the RIC or HC energies. Okay. The next question to ask is, well, so far we spoke about the electromagnetic field excitations in plasma, but what about the external magnetic field that is present there? What happens to this external magnetic field in the presence of the chiral magnetic effect? Okay. So in other words, this is my valence charges creating electromagnetic field in plasma at finite theta. How does the field look like? Well, again, schematically, you take these charges, external charges, take the chiral magnetic effect, and solve these equations. You can solve these equations, and it turns out that the effect of the chiral conductivity is to make the electromagnetic field oscillate as a function of time. Okay, as shown by this formula here. The second effect is that in addition to the phi component, azimuthal component of magnetic field, the radial and the z component also appear. So this is shown here. If the chiral conductivity is larger than the electrical conductivity of plasma, then the field exhibits these oscillations at other times. If it's small, then no oscillations. And perhaps this fact that there are oscillations is the reason why it's so difficult to measure the charge separation. Because if a magnetic field oscillates up and down, then on average, the charge separation would be zero. And it's one of the possibilities why it's so difficult to measure the charge separation. Now, if you look at long times and let the chiral conductivity fluctuate randomly, then what you see here, say on the right-hand side, is in the early times, the field oscillates rapidly, and then it flattens and becomes almost indistinguishable from the dashed line, which is when there is no chiral magnetic effect at all. So the dashed line is no chiral magnetic effect, and the solid line is effect. And the discontinuity here is just because I don't know how to compute the transition between when there are already important transitions between QCD vacua, but there are only few of them. So, but in early times, again, we see a lot of oscillations. Okay, so now that I tried to convince you that there's very interesting effects induced by this topological domains in quark-gluon plasma, we can ask the question, well, how can we actually measure, how can we study those domains? How can we study the distribution of matter on those domains and so on? And one time-tested way to do so is to shoot fast particles through that medium. Okay, you shoot the particle, you look how the particle interacts with the medium, how it radiates, how it loses energy, and so on. And then you conclude, you can make a lot of important conclusions about the properties of the medium. So then let's try to shoot a fast particle through quark-gluon plasma and see what happens. Okay. So this is a regular material, right? You shoot a fast particle through material. It radiates a Cherenkov radiation if the velocity of this particle is larger than the speed of light, the phase velocity of light in medium, right? This is Cherenkov radiation. And the transition radiation is when a fast particle crosses the boundary between media of different topological, different optical properties, right? So this is a figure taken from the particle data group in which they study the structure of the material by looking at the synchrotron, the Cherenkov and transition radiations together. Okay, so what is interesting in the chiral medium is that, as I mentioned before, the photon is not stable at finite sigma chi. So if you write down the equation for the vector potential and go to momentum space, you'll find that the dispersion relation for this 4 vector k is given here. So it's either positive or negative. And this opens the possibility to have 1 to 2 processes shown here. Either your charged particle radiates a photon, or photon splits into, say, quark anti-quark. In vacuum, it's impossible because energy conservation implies that k squared equals the right-hand side here, and you see that in vacuum k squared is 0. So this condition is never satisfied. However, if you have a chiral medium in finite sigma chi, then the right-hand side is either positive or negative, in which case you can have either pair production or photon radiation, depending on the sign of this combination. So for example, if sigma chi is positive, which I will usually assume in the following, then and lambda is negative, so left-handed polarization, then pair production can happen. But if the photon is right-hand polarized, then it can be radiated. So this obvious asymmetry between right and left, it's purely chiral effect. So to compute this transition amplitudes, you need to know the wave functions, of course, of each participant. For fermions, it's usual wave functions, and for photons, is given here. I'll employ here auto-relativistic approximation just because it allows me to neglect the instability I mentioned before, and it allows me to neglect the reflection from the walls and so on. It just makes everything more transparent, even though more comprehensive calculation has also been done. So the effect of this finite sigma chi is emergence of kind of mask term of this photon. Okay, so then you go compute the matrix element as usual, all these usual ingredients of the calculation times delta function. So this k perp squared is a combination of photon and quark momenta squared. It's always positive, of course. And this kappa lambda is a parameter given in this box. You see in vacuum, the right term here is 0. And so kappa is positive, delta function is never satisfied. So 1 to 2 process is impossible. However, in chiral medium, you have this additional term here. So when lambda sigma chi is positive and energy is large enough, this kappa becomes negative. And this signals the possibility to emit photon. So the angle at which this happens is proportional to the square root of sigma chi over omega. And this is purely the chiral Cherenkov radiation. So if you look at the particle going through the medium, at this angle, you should observe a maximum peak of photons radiated with given frequency, with given polarization. Okay, it should be either right-handed or left-handed. And then you go straightforward, through the usual steps and compute the photon radiation rate. It's 0 for one photon polarization, and it's finite for another photon polarization. Okay. Same goes for transition radiation. When a particle goes from a medium with one Chiral conductivity to another, it emits a photon. Okay, again, this formula can be computed along the usual steps. And if you look, in the textbooks on electrodynamics, you will find that this exact formula is true for a classical transition radiation. But however, here, of course, this this particular formula has a contribution from this pole, which is purely quantum effect that disappears when the H bar goes to 0. A little bit of phenomenology. What is shown here is the spectrum of this Cherenkov and transition radiation photons versus transverse momentum with respect to the direction of the fast particle. Essentially, it's proportional to the angle, radiation angle. You see a strong maximum at certain angle. X is the fraction of energy carried by a photon from the original charged particle. So this maximum signals the Cherenkov radiation, and you can see that the position of this maximum depends on the Chiral conductivity of the medium. Okay. So this can be used to study the Chiral magnetic effect in media, to study this Chiral domains in quark-gluon plasma or in other materials, in Weyl semimetal, that can be used, for example, to study the axion field in intergalactic space, right? If you look at the proton coming from the faraway galaxy, and it goes through the medium with finite axion field, that the proton should radiate then this Chiral Cherenkov radiation at the given angle. Okay, so this can be used as also another way to study the dark matter, axionic dark matter. Just an example. Okay, so as fast particle goes through the medium, it also loses energy, right? It loses energy for various reasons. For example, one of the ways is to ionizes surrounding material. It emits Cherenkov radiation and so on. And since we already know, I already showed you the calculation of the various components of electromagnetic field in this chiral medium, we can easily compute the energy loss, and it has been done by my student Jeremy Hansen this year. Essentially, we followed the Fermi model, the classical Fermi model, to compute the energy loss of a fast particle in medium, which equals to the flux of the Poynting vector through the cylinder shown in this picture. Okay, so since we know the components of the field, the two components are shown here. We know all others. You can check in our paper. And using the Fermi model for the electric constant, you can compute the energy loss. Now, if sigma chi is 0, then you recover the original Fermi result. At A goes to 0, when the radius of the cylinder goes to 0, you get then the total energy loss. When A goes to infinity, then you recover the contribution of the radiation. This is a Cherenkov radiation, which is finite only if the velocity of the particle is larger than the phase velocity of light in this medium. Okay. This is all known results, but we want to know what happens if sigma chi is finite. In this case, something interesting happens. If this is the energy loss, the first term is usual Fermi contribution at high energies, and the second term is purely contribution of the anomaly. And you see that it increases as gamma squared, as energy squared, and at high enough energies, it dominates and becomes larger than this piece. Okay, so the most of energy, high enough energies, is lost purely due to anomaly, right? Now, if you take A to infinity and look what kind of radiation is emitted, of course, you recover the Cherenkov radiation I just talked about. Okay, so this is the formula, and it coincides with the quantum calculation. If you neglect the recoil, what is interesting that if you look at these two formulas, the compute total radiation due to total power of the Cherenkov radiation, it's exactly this term here. So the amount of energy lost by the fast particle in the chiral medium at high energies is exactly equals to the power of the Cherenkov radiation. In other words, all the energy lost by this fast particle is due to Cherenkov radiation at high enough energy. Okay. So this is the calculation that we done for the parameters of the quark-gluon plasma. This is electromagnetic part of the collisional energy loss. It's small, but it's the QCD calculation looks very similar. So this bump here is the contribution of the Chiral anomaly, and notice the logarithmic scale. So this bump is a huge enhancement. In fact, if you integrate over all frequencies, you get that the energy loss due to anomaly is proportional to the energy itself, and the coefficient here is, it depends on the chiral conductivity, of course, but it can be pretty substantial. It can be up to so it can be so big that most of the energy is lost in a single Fermi. But again, we don't know the exact value of the chiral conductivity, and it would be interesting to compute it, for example, on the lattice. We did similar calculation for a Weyl semimetal, and just because in the Weyl semimetals, I think this experiment can be done easier than in quark-gluon plasma. So you shoot fast particle through the chiral material, such as a Weyl semimetal, and you see tremendous enhancement at high frequencies. So the expectation is that the energy loss of particles traveling through the Weyl materials should be much larger than in other materials of similar materials. So far I didn't discuss any coherence effects, right? Because we know that in the photon radiation, say in beta-Hatter process is modified strongly by the Landau Pomeranchuk-Migdal effect, where the energy dependence is reduced by square root of energy. This is still open subject, and the expectation, of course, is that since the relative contribution of beta-Hatter, relative contribution of conventional energy loss is decreasing, then the contribution of chiral energy loss should be more important. But again, this is an open question still. One interesting application of this to quark-gluon plasma is that since a single particle radiates in Cherenkov radiation, the whole plasma radiates as well, right? So the total, you can compute the total radiation due to chiral anomaly by the whole plasma by convoluting this fermion lines with thermal distributions, and you can show that actually the contribution of the Cherenkov radiation is comparable to the conventional mechanisms shown here of photon production by quark-gluon plasma. But further studies needed to get the more precise numbers. So the final part of my talk, if I have time, so if not, Igor, please stop me.
Go ahead.
I wanted to briefly discuss the transport anomalies from a somewhat unusual angle. So a model that I'm going to consider is proposed basically by this gentleman here, and it deals with, say, electron or any other charged particle scattering on a heavy particle in the plasma, and this process is mediated by a photon, which is modified in the presence of the Chiral anomaly. So this is the photon propagator derived from the Maxwell-Chern-Simons theory, where this B mu is has time component given by chiral conductivity, and a spatial component I set to 0, but in principle it's also the distance between the Weyl modes and the momentum space. You can take this into account as well, but again, for simplicity, I'll set it to 0. So the question is that how is the transport cross-section modified in the presence of the anomaly? Okay, that's a pretty straightforward problem to solve. I assume that the charge of this ion is E prime, magnetic moment is mu, and mass is very large M. So we can treat this as a scattering center. So the time component of this propagator is usual Coulomb expression. The spatial component is given here, and it depends, of course, on anomaly. So this B naught is sigma chi. The last term here is actually topological. So if you consider interaction of two constant currents, then the interaction energy is proportional to the Gauss linking number. So this is kind of linking configuration. The whole, actually, this whole expression is topological in nature, actually, but this last term gives this interesting, simple interpretation as the proportional to Gauss linking number. Given this propagator and given the current of this associated with this ion, we can compute the electromagnetic field created by this ion, right? So given this current, you compute the field, and then the question is, what is the cross section for the scattering of charged particle on this field? This is the result. You have the usual Coulomb contribution, familiar, and there is anomaly contribution. Okay? Notice that this pole in the denominator, which sits exactly when the momentum transfer equals the chiral conductivity, B naught. Okay? And this is another manifestation of this unstable mode of the magnetic field. The transport cross-section then is given by this formula. Again, the first Coulomb part is a textbook result. L is a Landau logarithm, while the second part is purely due to anomaly. And you can see that the second part is proportional to the momentum to the fourth power, while the conventional Coulomb piece is proportional to energy squared. So for high enough momentum, this term becomes larger than the Coulomb part. In other words, the transport cross-section due to anomaly is larger than without anomaly. And if you take, again, momentum to be big, large enough so that you can neglect the Coulomb piece, you'll find that the transport cross-section is given by this formula. Okay, it doesn't depend on how you regulate this resonance. It doesn't depend at all, and depends only on the magnetic moment of this ion and the chiral anomaly logarithmically. Okay, the large transport cross-section means small mean-free path, and it means suppression of the transport coefficients. So as a simple illustration of this, neglecting many important contributions, but just to illustrate the effect of the transport cross-section, is this calculation of the electrical conductivity. And again, I neglected the anomaly contributions to this distribution F naught. So the effect of the large transport cross-section is that decrease of the conductivity with temperature. Okay, only the Coulomb piece is given by this dashed line, while this dotted line is dotted line is gives this decline with temperature. Again, this is a prediction that can be verified experimentally. Okay, I think I already spoke too much. Let me summarize. The electrodynamics of chiral media, such as quark-gluon plasma, wire semimetals, axionic dark matter, primordial magnetic fields, just to mention a few, has many novel effects and intriguing features. I mentioned only a few of them, those that I personally worked on and interested in. There are many interesting, exciting opportunities for ambitious experimentalists, and I welcome everybody to think about this and ask me questions. Thank you.
Thank you very much for the presentation. We now have some time for questions. So let's start with Pavlo Sukhachov.
Thank you very much for this nice talk. I have a question regarding the Weyl semimetals part. So, do I understand correctly that during the calculation of the transition radiation, no surface states were taken into account? So, to which extent the condensed matter physics is taken into account in your calculations?
So you asked if I took into account the surface currents in the transition radiation calculation?
Yes, for example, contribution from the Fermi arc surface states. Are they important?
The answer is I don't know. At high energies, they should not be important because all these effects, the currents that are induced on the surface of between the two media is of much, I'm trying to think about a parameter to specify. It should be small because energy of this particle going through this medium is so high that the deflection that experiences is small. Okay, I think that the currents induced there would be proportional to this deflection on the surface. But in practice, in practical measurements, it should be important. But in this particular limit of high energy, it is not important. That's what I'm saying.
I see. Okay, thank you.
Okay, let's go to the next question by Graziano Mileta.
Thank you for your talk. Okay, in slide 13, I saw that the calculations led to 4 different solutions for the pulsation. Mm-hmm. But is any of these solutions real? If so, can this solution be linked to some phenomenological characteristic of the medium?
Okay, I think this is the slide you mentioned, right?
Yes, yes.
Yeah, sure.
We have a 4th solution.
Yeah, so this has been discussed in literature. The phenomenological implications of this instability is very important. For example, it is believed to be responsible for the large-scale magnetic fields in the universe. Possibly, it can be also. It plays a great role in various models of early universe, cosmological models. Now, in the heavy ion collisions, I believe it doesn't play an important role because it doesn't have simply not enough time to develop it. Okay, because the sigma chi, which sets the typical time for the evolution, typical time for the instability to develop, is just too small. So the corresponding time is too large in heavy ion collisions. Okay, but as a question of principle, say in a star, right, it would be more important. Any stable system that lives for a long time, this instability plays an important role.
Okay, thank you.
Okay, next question to Masoud Shokri.
Thank you for your very nice talk. I just want to ask 2 questions, if possible. And first is that as you showed the photon propagator, so even in 3+1 dimensional Maxwell-Chern-Simons story, we can say that the photon is massive, yes?
Mm-hmm.
Okay. I just wanted to confirm that. But another question is about the, I mean, I think in most of your works and other works on Maxwell-Jones harmonics, the gradient, the spatial gradient of theta is assumed to be 0. But I mean, if you can you imagine that in a droplet of quark-gluon plasma, the theta changes between the fluid parcels. Can this be true? Or
Absolutely.
this is okay?
You're absolutely right. Yeah.
And it seems that if that is the case, the an anomalous Hall current is produced because you will have some electric field or at least electric fluctuations. And recently we have tried this this setup and assume that this divergence is not the gradient is not 0, and then an instability arises that the modes are causal but are unstable. Do you think if that is the case, if our calculations are correct, I can send it in the chat, it means that something is wrong about this MCS story?
I think that, well, first of all, to address your question about the finite B, absolutely, the B is important. We know that this homogeneous solution is just an approximation, just to feel what's going on in the system. Right? It allows us to have a simple model to play with. But B is important, and in fact, in the Weyl semimetal, this is what drives the whole effects. And in fact, this gentleman here I mentioned in my slide, they discussed it in detail too. And in one of my papers with my collaborators, we did this as well. We basically solved the whole problem of instability at finite, not instability, I'm sorry, the electrodynamics at finite B, okay? And we found the same, very similar, I would say, chiral Cherenkov radiation. If energy of the particle moving through this medium is higher than this B, much higher, then it doesn't feel any anisotropy. So the radiation then is pretty much very similar to the radiation in azeotropic medium. Okay. Of course, it depends on the orientation between the direction of the angle between the direction of fermion motion and the B vector. Okay, so of course the whole radiation depends on that, but otherwise there's very little dependence on anisotropy. Again, so we can solve and find this solution with anisotropy. However, you're right that there is no instability in the finite B.
Thank you.
Yeah.
Okay, next question, Ho-Yi.
Thanks for a nice nice talk. Can I ask why you call this energy loss by Cherenkov radiation the collisional energy loss? Do we need collision to have Cherenkov radiation?
Yeah, it's a good question. Yeah, it's somewhat, well, let's say I maintain the tradition. So Fermi called this collisional energy loss, and see, the Cherenkov radiation, even without all these chiral nice effects, is part of this collisional energy loss, so to speak. And in the Fermi model, it arises as a part of the energy loss by a particle moving through the medium. And that's why I continue this tradition. I am calling this collisional energy loss, even though you're right that it's somewhat misleading. Absolutely. It actually confused me originally too, but yeah, it's a radiation and energy loss. I would call it, right? But,
so just to make sure, do you need any collision with background particle to have
no
Cherenkov radiation? No.
But it's interesting that it arises in this model of the collisional energy loss.
Yeah. Thanks.
Okay. Next question, Tanmay Vachaspati.
Yeah, I wanted to ask about this Cherenkov radiation too. I mean, you said that, say, cosmic rays in the form of protons would emit Cherenkov radiation and lose energy. So that, if there were axions, then there would be some sort of cutoff on the spectrum of protons. But we observe these, we don't, I guess there might be protons or heavy nuclei, but in any case, we observe very high energy cosmic rays. So that must place some constraints on the axion model.
Yes.
What are those constraints?
I don't know. I don't know.
Has anyone
Not that I know. Maybe I don't know. I don't think so. I think that's open question, and I personally didn't check it. We published the PRL, I think it was a year or two ago, in which we discussed that this should be the case. There should be constraint on the axion field, but we didn't check that.
That would be very interesting.
Absolutely.
The other question I had was about the monopoles that you talked about. These are color monopoles, right? They're not electromagnetic monopoles.
Right.
And so there's been some papers on the Schwinger production of magnetic monopoles in heavy ion collisions. I don't know if you're aware of them, but since these are color monopoles, are there strong color magnetic fields as well?
Yes. Thank you for listening to me, attentively. Yes, I little bit, I brushed it under the rug a little bit, but thank you for pointing this out, dragging it out. Indeed, the model that I presented assumes that everything is electrodynamic, right? And so what we did, we said, okay, let's suppose we have magnetic monopoles in QED as a model, as an abelian model for QCD. Okay. So our model involves QED monopoles, essentially. And then presumably it should the same be true for QCD if you generalize everything, because you see, most of the discussions in this talk were about the Chiral anomaly in QED. But in principle, gluon fields coupled to this topological domains exactly the same way as QED. So at the tree level, the only difference between QED and QCD would be just the color factor and coupling constant. So many of the conclusions still hold for QCD, but you're right. The model was a purely QED model, yes.
Okay, thank you.
Okay, any other questions from the audience? I do have one question of my own, actually, also regarding Cherenkov radiation that you are discussing here. When you're talking about this, typically Cherenkov radiation is not for the photon moving through the charged plasma. If it is moving through a charged plasma, it's actually not a photon, it's a plasma. Wouldn't that drastically change this and basically remove this effect completely?
Yeah, so, okay. The interesting point is that, right, so Cherenkov radiation is usually discussed in various dielectric materials, right? So basically what I did here in this slide, maybe I skipped it too fast, but I removed all the bound states. There's no bound state at all, just for simplicity of presentation. It is plasma. Okay? And so while the original Cherenkov radiation has to have go through the plasma, through the usual material, as you mentioned, the chiral effect doesn't depend on it. It depends, but it still remains finite, even if you remove completely any bound states.
No, but this is not about the bound states. This is about the fact that epsilon is not a description of electromagnetic wave propagating through this material. It's a plasmon, which is gapped mode. That epsilon plays no role when you have a gapped mode.
Yeah, so, okay, so our model for this, for the epsilon is given by this form. Basically, put omega naught to 0, put gamma to 0. So this is simple plasma frequency, the only parameter that plays role here.
I see. Okay, I have to think about that.
Yeah.
The reason I'm asking is actually because essentially you need this velocity to be greater than the speed of the photon, but
Right.
for the gap plasma, it sort of seems not the most relevant parameter. That's why I'm a bit confused.
Well, this Chiral effect, it doesn't depend on at all. I mean, in the usual case of Cherenkov radiation, see it appears here the square root of epsilon naught in the Fermi model. Nothing like that appears in if you have Chiral Cherenkov radiation. So in some sense, it doesn't belong, as I already mentioned, it doesn't belong to the as the collisional energy loss. Of course, particle moving through the medium losing energy, and this is part of that. But this is not what we usually call the collisional energy loss.
No. That is perfectly fine. The plasma is also not collisional. It's actually completely collisionless mode, but somehow I thought it would change the discussion of the Cherenkov radiation. Anyway, this is probably something we have to sort out sort of separately. We have another question from Graziano Mileta.
Okay, thank you. Another question. Maybe I haven't seen it. Have you ever calculated by imposing suitable conditions a possible solution for the potential vector Ha?
Calculate what? Excuse me. Sigma hat? Sigma chi?
No, for the vector potential. Have you a solution?
In medium?
In medium, yes.
Yeah, sure. We computed all this. I mean, we computed all the fields, E and B fields in medium. Yes, we did.
What is this form?
Well, you can see here, for example, I just anticipating this kind of question, I wrote a couple of the components, and they're not terribly complicated. I mean, it's algebraic expression, right?
Indeed.
It's K1 is some modified Bessel function and polynomials. We integrated over it, and this is the result. The nice feature of this Fermi model that it can be solved analytically. Yeah, so you can check it. It's classical and solvable.
Okay.
Are there any other questions from the audience before we wrap this up? I want to use this opportunity once again to thank our speaker, Kirill, for a nice presentation, taking time to answer the questions. And with that, we will stop the official part